Can everyone hear me well? Excellent. Thanks, Melissa, for the introduction. And, someone just told me this morning that you guys had a fire alarm because my topic's too hot. I hope that's the case. All right, so I hope everyone's been enjoying our winter school this week so far. Certainly, all the lectures we put together and chat discussions, hopefully. So my name is Yi Huang. I'm a senior lecturer from the University of Melbourne, and I'm an atmospheric scientist and also chief investigator of CLEX. My expertise is mainly in cloud, precipitation dynamics, and physics. I also do high-resolution weather modeling, as well as atmospheric remote sensing. So I think it's great to have this opportunity today to talk to you a little bit about the high-resolution modeling. As I said, I'm an atmospheric scientist, so apologies to those of you who probably study ocean or land more in your research. But I think, as we know, our climate system really is strongly coupled. So hopefully what you learn from this lecture today will also be relevant to the research you're doing. So, okay, I think everyone sitting here today in this room probably agree with me that our climate models certainly have been tremendously helpful in sort of revolutionize our knowledge of our climate and climate change science in the past several decades. But I believe many of you probably also come across, some of the discussions about probably the most outstanding open problems in climate science as well, right? Such as, how do our atmospheric circulations expected to change in response to climate change, right? And how do our severe weather behaviors might change in a warming world? So quite fundamentally, many of these outstanding, open kind of problems in climate sciences is, strictly linked to some of the basic, but also kind of well-recognized deficiencies in our climate models, which in part, due to how these models were formulated in the first place, and due to mainly, computational constraints. But over the past 10 years, 20 years or so with technology advancement, the computational limitation is starting to fall away. And we're kind of entering into a new era where a new model quality, and that's a modeling framework that can be run at high resolution, is just becoming more and more commonly used. So today I will just take this opportunity to bring you to this high resolution modeling world. Just to show you, how this powerful tool has been transforming the way we study weather and climate. So I decided to structure, this lecture around 5 sort of questions I think important to address. I'll start by answering a question: why exactly do we need high-resolution atmospheric models, and then talk a little bit about, what is in these models, what they're made of, how are they formulated. And then I'll give a really quick overview of, just history and how these kind of models are developed, and to which purpose they've been applied to. And then I'll talk a little bit about, what I think could be the future applications. Okay, so why do we need high-resolution atmospheric models? So what I'm showing here is a table I took from, a recently published research paper by a group of CLEX researchers, where they undertook a qualitative assessment of our ability to observe, to understand, and also to realistically model a range of extreme phenomena in Australia, using our climate models. So as you can see in the table, they examine a wide range of extreme phenomena. And I just wonder if I got the pointer here. Oh, wrong one. Oh, this one, yes, back. A wide range of, extreme phenomena here. And in this assessment, L here indicates, low confidence, M indicates medium confidence, and H indicates high confidence. So what they concluded in the study is that obviously our climate models are able to simulate, many of those large-scale heat events, both over land and in the ocean, reasonably well. However, many of these what we call the mesoscale convective systems, such as like East Coast lows and tropical cyclones and severe weather. These are really the systems that generate high impact weather, are currently beyond the capability of our climate model to robustly simulate. Well, the question is, why is that, right? So I think to answer that question, it's worth just having a quick look at exactly how our climate model works. I think some of you here must been working with climate models, so you probably already have some understanding, or basic understanding of how climate model works. So a climate model essentially is just a very complex mathematical explanation or representation of our very complex Earth system. So in a climate model, the Earth's surface and the atmosphere are basically divided into a three-dimensional grid that looks like this, right? And each grid just represents a specific volume where variables like temperature, pressure, relative humidity, winds are calculated. So the size of each of these grid cells is what's known as spatial resolution or grid spacing of our climate models. And for the climate models commonly used, such as those from the SIGMET group, they typically have a spatial resolution of about 100 kilometers, right? So it's basically a 1 by 1 degree box. That's pretty big because many of these atmospheric processes that underpin the development of thunderstorms, severe weather, are actually happening at scales much smaller than the climate model grid lengths, right? So because of this, our climate models are not able to directly simulate or explicitly resolve these processes. And the way that our climate model deals with that is to parameterize them using some simplified approximation based on usually observational data or empirical data or the smaller scale model. But the development of our climate model actually has come a long way. So here, what I'm showing is, this increasing resolution of climate model that's been used through our first 4 IPCC assessment reports. You can see, these topography details really start to emerge as you increase the spatial resolution, right? And also the vertical resolution has been increasing over the years as well as part of a model development. And in fact, in some of the latest climate model we're using, the grid spacing really has been, decreased down to around 70 kilometers, and with, much more levels in the vertical as well. But of course, that comes with, a significant increased computational cost. But even with, these increased resolution in our latest, generation of our climate models that are widely used, they still can't resolve, many of these processes underpinned our high impact weather development. And this is because here I'm showing this diagram on the right where you can see the space and time scale of a wide range of our dynamical processes in the atmosphere, ranging from micro scale to mesoscale to synoptic scale to global scale, and spanning from minutes to hours to days and months and years. And you can see clearly that a lot of our high impact weather associated with these systems like tornadoes and thunderstorms and front scoreline, they're happening at scales of around a few kilometers to just several tens of kilometers, right? Still much smaller than what a traditional kind of climate model could resolve. And also these systems, this weather system, they develop and evolve very, very rapidly, much faster than what can be captured by the time intervals that are used by these successive calculations to update the model states in the climate model, right? So that's really the challenge. So in order to directly simulate these kind of events, we'll have to go for higher resolution atmospheric model, right? But what exactly is high resolution? Right? What does it even mean? Especially if we consider the hierarchy of the atmospheric models being developed to capture, the scales of the atmospheric motion from, as you can see here, millimeter scale, and that's where you could actually represent individual cloud particles and interaction to the planetary scales, where you could represent those planetary waves. But here in this lecture today, we're just going to focus on this specific range of scale around a few kilometers, usually somewhere between 1 to 5 kilometers, and that's what we call the cloud resolving scale or convection permitting scales. And this is the scale where you could realistically represent things like this, mesoscale convective cloud systems that look like this, as well as some individual clouds, including this fair weather cumulus that look like this. Just to put this in perspective, I'm showing this photo that's taken from a research aircraft, which kind of capture the different elements of these clouds within a mesoscale convective system. So what we could see here is this deep convective core of the convection, and also this turbulence eddy at the edge of the cloud. You could also see this high-level kind of envelope clouds as well in this picture. And these are all commonly found in our mesoscale convective systems, such as score lines, such as organized convection. And here on the right, it's just to show you conceptually, how these kind of cloud systems were captured on the top within a climate model script box, right? And also by our high-resolution cloud resolving models at the bottom. Now, what I think is really cool about high-resolution modeling is that you don't need to be a scientist to be able to appreciate the beauty of this amazing level of detail. So here I'm just showing an example of a 3D rendering of this simulated cloud data in an artistic setting, where you could actually see the beauties of these high-resolution simulated clouds through the lenses of an artist, which I think probably less scientific, but a lot more attractive in some way. Okay, back to our cloud resolving models. Our cloud resolving models actually known by several different names, depending on the specific application characteristics and also the context in which they're used. So apart from cloud resolving models, sometimes in the literature you'll see cloud ensemble model, convection permitting model, cloud system resolving models, storm resolving models, and convection allowing models, right? Just some variation in the naming, but by and large, they all referring to the same thing, which is a numerical model whose grid spacing is fine enough to allow explicit simulation of many important features of convection. Okay, so that's a little bit about the naming and of this model in the background. Now you may wonder, what's actually in these models, right? What makes them so cool? What are they made of? How are they formulated? So this is just a simple kind of summary of the key structure of a cloud resolving model, right? Obviously, we will have to have the high resolution grids to begin with. But essentially, these kind of model consists of, first of all, an advanced dynamical core, right? And then it's accompanied by a few kind of packages that we call the parameterization to represent the physical processes that are not resolved by the model. And these include primarily the microphysical processes, subgrid scale turbulence, and radiation. We also need the boundary and initial conditions to drive the model, right? The initial conditions usually derive from our observational data set or larger scale model outputs, whereas boundary conditions reflect the influence of our large scale atmospheric flow. So this is just a more detailed look at all these core components. And first of all, again, we have the dynamical core, This is extremely critical because this component is responsible for solving, the range of the equations that govern the atmospheric motion, right? And these are affected, obviously by convection, by turbulence, microphysics, radiation, and also surface fluxes. And then once again, we got these parameterization schemes. Microphysics is designed to, represent or simulate the effect of cloud processes, including like the formation, growth, and the precipitation of the cloud particles. The microphysics representation in many of our cloud resolving model nowadays is still highly uncertain, I'll have to say. So your simulation sometimes is quite sensitive to, the particular microphysical scheme you choose. And then the subgrid scale turbulence is the parameterization that represents the small scale turbulence and the mixing within the atmospheric boundary layer, as well as in clouds. And this is also quite an uncertain process in our model. And finally is the radiation, which simulates the interaction of our solar and terrestrial, which is just the short wave and long wave radiation with the atmospheric components, including clouds and aerosols. Now, there are a variety of schemes that you could choose, but sometimes it could be very, very expensive to run. I could say this is probably the most expensive part of the cloud resolving model in the simulations. All right, let's just take a deeper dive into these individual components. The dynamical core, right? So what do we need in terms of the basic equations? Well, first of all, the first equation we need is the equation of the state, which represents the thermodynamic state of the air. And then we need a continuity equation that represents the conservation of mass. The third equation we need is the dynamical equation, for the conservation of momentum, that basically describe and govern the motion of the atmosphere in terms of horizontal and vertical wind. And then we need a thermodynamic equation to represent the conservation of heat. And finally, we will need a moisture equation to represent the conservation of water. All right, so this is to describe, the transport and the phase change of like water vapor, cloud liquid, and ice particles, things like that. It's really, really important to know that the dynamics is non-hydrostatic in our cloud resolving models, which means that the fluctuations in a vertical wind cannot be neglected, right? So this is what fundamentally differs from, our traditional large-scale climate models, which is based on the hydrostatic assumption, which means that the vertical acceleration, of the wind is completely ignored. But we know that it's the vertical acceleration of the wind, or in other words, the updraft, that really underpins the development of severe weather, like thunderstorms. So this is really, really important, and the biggest difference, I think, between our cloud resolving model and the traditional global climate model. So now let's have a closer look at these equations. I promise it won't take long. So first, the equation of the states, which represent, the interaction between the temperature, pressure, and the air density. Then we got the continuity equation, which relay the change of, the density to the convergence, divergence, of the winds. Then we got this dynamic equation, right? Here that governs the motion of the air, which is driven by, several terms you could see on the right. You're probably familiar with some of these terms if you're using large-scale models. For instance, we got the pressure gradient terms, the Coriolis terms, and this is pretty much the same in the large-scale model. But here we also got this advective and turbulent fluxes term, and importantly, we got this buoyancy term, and that really is a result of this non-hydrostatic assumption we made, allowing the vertical acceleration of the air. And then we have this thermodynamic equation. Once again, the change of the heat in the system is driven by several terms. And similarly, we have this large-scale advection. We also got this advective and turbulence fluxes. But there are these two extra terms, taking into account the radiative heating due to the radiation process, and also the heating from microphysical processes, such as, the latent heat release. And finally is our, moisture equation for the water vapor and the hydrometeor species for the conservation of water. So in the equation on the left, R here represents the mixing ratio of our individual hydrometers, and these are the, liquid drops and, ice crystals and snow particles and gravel, hail, these kind of things. And that's driven by these several terms on the right. Once again, we can see this large-scale advection term, advective turbulent fluxes, and finally, these microphysical sources in sink, which I'm touch on in a little bit. Okay, so these are all the equations I want to go through, promise. Now, let's talk a little bit about the physics. So the physics here, what I refer to really is the physical parameterization that we discussed at the beginning, which represent the exchange, of the energy between the atmosphere and the other sources. And these are the processes, once again, happened at, the scale smaller than the model can resolve. So, these are like cloud formation, precipitation development, turbulence in the boundary layer, and, energy exchange. So in summary, these are the microphysics, the turbulence, and radiation. So the microphysical parameterization is designed to represent many complex exchange, between the different types of hydrometers, as I mentioned. Our cloud liquid drops, our ice crystals, our, snow particles, gravel, hail particles, etc., etc. They all come in different, size distribution, different shape, and, different concentration as well. And also, there are numerous microphysical processes happening in convective clouds, and particularly in those deep convective clouds. It's kind of illustrated in this diagram here on the left. Particularly when the clouds developed, below the temperature of freezing, that's when you have the ice processes kicking in. So you not only have to worry about things like condensation and evaporation for the warm part of the cloud, but also the various ways of glaciation, sublimation, entrainment, with the clear air, and also how these processes interact with the atmospheric circulations and the aerosols in the background in some cases. So not surprisingly, the microphysical processes are still not completely understood. So, their parameterization is actually extremely difficult, but also extremely important. So microphysical parameterization come in, different forms depending on the level of complexity you like to have for, the events you want to simulate. And they often differ in the way they specify the different hydrometer types and the different processes they considered, and also different in the formulation of these processes as well. But the most commonly used microphysics scheme are usually, in these two types, the bulk scheme and the bin scheme, and that differ in how they actually, represent the size distribution of the particle. And for the bulk scheme, we also have single moment, double moment, and in more recent years, people have, developed a multi-moment scheme that basically different numbers of moments represent the different numbers of the prognostic variables these schemes have developed to describe the properties of the, hydrometers in the atmosphere. But generally speaking, the bulk scheme is, more like, I guess, computationally efficient to run, so it's more commonly used in our operational setting, such as in our weather forecast model used by the Bureau. The bin scheme is a lot more expensive and it's usually, applied in the research setting that provides additional kind of deeper insights into the microphysical processes. So the pictures on the right, and, just give you an idea of what a simple scheme looks like and what a sophisticated scheme looks like, fundamentally. And then we move to the subgrade scale turbulence. Just similar to the microphysics scheme, they also come in different forms and different level of complexities. I'm just quickly showing you, an example of one way to parameterize the turbulence, and that is to express the turbulence flux on the left, as a function of the local gradient of the mean quantity of our meteorological variables. Right, so that's one common way to do it. And then very quickly on the radiation, once again, that's the parameterization scheme that tried to describe the interaction, between these short wave and long wave radiative transfer in the atmosphere and how it interacts with the environment, including like clouds and aerosols. And similarly, they also come in different forms and different levels of complexity. We got this broadband kind of scheme that consider a limited number of spectral bands, electromagnetic, bands. And also we got this commonly used two-stream approximation that split, the radiation into one is downward and the other branch is upward. I just want to mention that, clouds could have significant impact on the radiative transfer because of their different size, different shape, and different number concentration. You could imagine, how the different particles, could have a different way to scatter the sunlight. And that's exactly the reason, right? So when you do this radiative transfer calculation, you do have to take those factors into account. Okay, so that's all I want to, discuss in terms of like what's in these models and how are they formulated. I think this is, very important kind of basic understanding of how it works. Then I will just talk a little bit about, I'll be quick on this, about the development of these kind of models historically. So, because of the, rapid advancement of our, computation technique in the past several decades, we also see a significant advancement, in this cloud resolving model development and their application in the atmospheric and climate sciences, which I think could be characterized by these several phases that I try and summarize here. So, as we probably know, the early development of our numerical model predictions actually happened during, about 1950s to about 1970s. And this is when we had the first attempts of developing this cloud resolving model as well. And this is also a time when there's some rapid development of our convection parameterization. And then it comes to, 1970s to 1980s, and that's when the mesoscale models were started to be developed. Our very first cloud resolving model was actually born in this period as well. And then during the 1990s to 2000, we saw some really rapid advancement in computing and also in the model complexities as well. And that's a period when we saw some rapid development in detailed cloud microphysics, physics in general. And there are also a lot of field campaigns, happening during that period of time with aircraft observations, ship observations, ground-based observations, which collected a lot of, in situ observational data that help develop, our models, our, parameterization, and also to help validate these simulations. So in the past 20 years or so, we saw, a significant kind of trend in terms of integrating, these high-resolution cloud resolving models with large-scale models, right? We're talking about global models in this context. And we also see, more and more use of the high-resolution simulations in a lot of applications. And we saw the development of couple model, and that's the coupling between the ocean, the land, and the atmosphere. And finally, what about the, the current trend and future direction? So what we're seeing right now is probably that's, what some of you have been doing or working quite actively on right now is to incorporate machine learning into improving, some of these models and developing parameterizations. And also we have improved observational system to also help improve this modeling framework. And finally, we saw more and more applications of this cloud resolving model in climate change related research. So that's just a bit of history of its development. Now I want to talk a little bit about the purpose, to which purpose these models been applied to. Right, we're saying that they're being more and more increasingly used, but what are they used for? So I think, as I said, over the past 20 years, and there's significant advancement in this model development and their application in atmospheric and climate sciences. And in the interest of time, I'm not going to really give you a long overview of this topic. I'm going to just, I guess, show several kind of key applications here, but noting that what this model can be used for is actually far beyond what I'm going to show in the next few slides. All right, so one common application is to use this model to study cloud dynamics. All right, so here I'm showing this example taken from a paper where they use the cloud resolving simulation to examine the role of vertical wind shear in the mesoscale organization of a convective scoreline system. Right, so the researchers look at the wind shear, which is basically, the change of wind speed and direction with height. Okay, so they ran two experiments. One on the top is an experiment without a wind shear, and then the second one is with the wind shear in the lower troposphere. And here what we see is a snapshot of a cloud, which is represented by the gray volume, and the near surface air temperature in color shading. And what they found is that when we don't have the wind shear, you could see these isolated convective clouds development in the model, but it's kind of scatter across the model domain in the top. But when you introduce the wind shear, you could see that these clouds start to magically organize themselves into this a score line type of system. So they're becoming more and more organized. So they concluded that these simulations basically suggest that the wind shear is probably play a very important role in the organization of this convective mesoscale weather system. So another common area is to use them as a test bed, for developing and validating our parameterization, in particular the convection parameterization used for large-scale models. So here I'm just showing you once again a study where the researchers ran many cloud resolving simulations to derive a quantity called the mass flux, and that's a really important quantity used in the convection parameterization that describe the vertical transport of the mass. All right, so these researchers ran many experiments for a variety of cases, and then to derive statistically the mean profiles of these mass flux related to the different kind of environments associated with the convection. Another common area we could see this application is, to improve severe weather forecasting, right? So this is just a case, where the cloud resolving models to use simulate this, tropical cyclones, right? So you could see, this is the simulations using these high resolution models, where you could clearly see, the structure of the cloud band, the spiral structure of the cloud band, and also importantly, the eye and eye wall structure of the tropical cyclones quite clearly. And if you compare this to the coarse model resolution, and this is really the climate model scale, about 100 kilometers, and these features just almost completely absent. So another application is to use it to study precipitation development processes. Here I'm just showing you this a recent study we published where we use a cloud resolving model to study this precipitation development, including the development not just on the ground, but actually within the clouds that involves the droplets and raindrops, cloud drops, and also ice particle development in these dynamical environments. Looking at the precipitation development associated with the passage of a cold front over our snowy mountains, right? And you could also examine the interactions of these different hydrometer particles with the mountain topography as well. And finally, I'm just showing an application on the climate change research, right? So as I just mentioned earlier, this is becoming a new trend where people could start use this high-resolution simulation to answer some really important climate change problem. So in this study, 7 different cloud resolving models have been run many times to derive this mean profile of the subtropical low clouds. They want to answer the question how these subtropical low clouds are going to change in response to global warming. And that's a very, very important question to answer because we know that these low clouds could either amplify or damp the climate change, depending on how they interact with the radiation. So here what they are showing is, the solid line is what these cloud structures look like in the current climate, and the dashed lines are what these clouds look like in a warming climate, under different scenarios and things like that. So here locally, I think in the center, our Klex and Molling kind of team has also been at the forefront of developing a national capacity to use these high-resolution cloud resolving model to examine our weather across Australia. So we've got this project called AUS2200, some of you probably heard of already, and that really is a project that aims to develop this cloud resolving capability, with model spacing at 2.2 kilometer grid spacing across Australia and around to using our Australian access model. So this platform is actually intended for our researchers and model developers to use to better understand the atmospheric processes underpinning our weather development across a wide range of scales, of course. So on the right, I'm just showing an animation of an event, the flood events that happened a couple of years ago in Lismore, where we could capture the kind of atmospheric processes, from this large scale to all these local scales. Some of you probably still remember this record-breaking flooding event. And in addition to that, we also ran, quite a number of experiments capturing, different events and studying a full range of weather, ranging from, the bushfire weather to all these flooding and extreme rainfall events. We also had some months-long simulations to capture the tropical intraseasonal variability as well, and the related atmospheric processes. I won't go through them in detail here. But just to quickly show you, how our center researchers have been using this model. So this is a study led by our postdoc Human Hayek, where he used these simulations to examine the role of the atmospheric dynamics in drying the atmosphere in the boundary layer during this 2019-2020 Black Summer bushfire events in Southeast Australia. So what he found is that, using this high resolution details, he found this important role of the convective role in the boundary layer, which brings these really hot and dry air from above the boundary all the way to the surface, during this strong mixing period, right? And that creates really dangerous fire conditions for the bushfires to develop. And another study, is to look at rainfall extreme event, and this is the events associated with a really complex East Coast low that developed, back in 2016 that affect almost the whole area of Southeast Australia, including Tasmania. So this is led by our center researcher, Chris Chambers, where he used these simulations to look at the role of these, warm currents along our southeast coast, as you can see here, compared to the climatology. So during this event, we got this stretch of the warm currents, and he ran two simulations. So one is without these currents, and one is with these currents. And he found that this warm current along the southeast coast play a role in, producing and reorganizing these low pressure systems affecting the southeast of our continent, and also play a role in redistributing the rainfall as well during this event. Okay, so I think just to finish off this lecture, I'll just share probably a little bit of a perspective in terms of what the application in the future could be. So I mentioned earlier, in the past 20 years or so, we really saw a very significant development of, either the computation as well as, applying this cloud resolving model to a global scale, right? So the first global cloud resolving model was actually invented, I guess, exactly 20 years ago. But over the past several years, there are more and more groups around the globe starting to adopt this approach. And now this framework, the global cloud resolving model framework, is becoming in more active use. Okay, so just to give you a little bit of flavors of what they look like, I'm showing you here 6 images. One of these images is actually a snapshot of our satellite observation, okay, real satellite image. And the rest of them are actually the synthetic images produced using our global cloud resolving model outputs from 5 different models. Can you tell me which one you think is the real satellite images and why?
The middle one on the bottom.
This one?
Not bottom.
This one?
Yeah.
Why is that?
Australia is a different color.
Australia, different color. That's a very clever answer. Does everyone agree, though? Does everyone agree, though?
Also, the ocean has colors. Yeah. Around.
They could be using different rendering technique depending on the group.
Shallow ocean coloring.
Shallow ocean coloring. That's a very clever answer. Any other answers? Top middle, this one, and why?
It's not too patchy.
It's not too patchy? You think patchy is a bad sign? Bad simulation?
Maybe.
Any other answers?
I think I could say the reflection of the sun in the bottom middle as well.
Reflection of the sun? Excellent, okay. So yes, so what's the correct answer? That's right. But you're probably not focusing on the clouds much. But anyway, I think that's a very clever way of looking at it. Honestly, I couldn't get it right in the first place myself. So I think this is an example that's really showing, how strikingly, remarkably, realistic these simulations look. It doesn't say that these model simulations are perfect. They're nowhere near perfect. But this is really, the realism of the simulation really, I guess suggests that there are a lot of potentials in these models, right? And honestly, I think these kind of model will become a major type of our global atmospheric modeling framework in the decades to come. So finally, I just want to, quickly show you this, what they call the top 10 advantages of a global cloud resolving model, and these are the ideas that summarize kind of by our modeling research community. These are not my ideas. I'm not going to go through them because most of them are actually saying exactly how wonderful these simulations are for understanding atmospheric processes for a wide range of scale, which is true. What I want to just note here is at the bottom, really is I think these kind of modeling framework is really opening some quite exciting new opportunities, not just in atmospheric and climate sciences, but also just if you think about how expensive it could be to run these high-resolution model across the globe, how much data you have to store and analyze and understand, this would have to evolve like computing science, data, information science as well. So this will really excite, a broader community and encourage new technology advancement. So I think I'll just end there. Thank you very much.